IC, and this current will be IB, RB, and this resistance is RE, and current here will be IE. Now tell me, this is BCE plus minus, this is VBE plus minus. Now tell me.
So after taking the input to outputness RB at a point where IC and IB at that point current divides na sir IB this one IC na sir.
No, 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 no. This current is IC current, okay, and this current is IB. This is simple. I can correlate. This is like this network. If I say this is IB, if I say this is IC, then this will be IE. Understood?
Okay sir.
Okay, and one more thing, one point is there. Here it seems like this is in case of transistor, this will be IC here. Here it will be IC only. Understood my point? At this point it will be IB because this is emitter terminal. So here it will be IE. So IE will be combination of IC plus IB. Understood my point?
Yes sir.
Excuse me, sir.
Yes.
Sir, whatever questions are that were given in previous.
Yes.
What will happen when you added a 10-volt battery?
Hmm.
Sir, actually, I'm not getting what is the purpose of that 10-volt battery. What will happen to the circuit?
Okay, I'll explain. Anybody solved that numerical problem, whatever I have given you? And you know well, you drive this stability factor by yourself, and then now we are going to calculate the stability factor for different biasing. Okay, and for potential divider biasing, the equation for input equation minus BTH minus plus IB RTH plus BBE plus IE RE equals to 0. Do you remember this equation? Yes. Actually, we remember the circuit of potential divider biasing after making it a Thevenin's equivalent circuit. Okay, fine. And once I remember the circuit, then without having some exact circuit in on my copy, I can write any equation directly. Okay, this is IC and this current is IB and this current is IE. And this is BCE plus minus and this is VBE plus minus. Okay, fine. So I wrote this equation and this is BTH and this is RTH. So this B minus BTH plus IBRTH plus VBE plus IER equals to 0. Understood? So I was having circuit in my brain, so that's why I have written this equation directly. Okay, so you also do some similar kind of exercise that without having circuit, without drawing circuit on your copy, you start writing equations directly. If you are able to do that kind of exercise, that in that manner you can understand that you can think of yourself that you are expert of particular biasing and related circuits. Fine, and here if I say the potential divider biasing, so if I differentiate it in respect to IC, because beta I know generally for finding the stability factor I have with IB. If I differentiate IB if a whole equation in respect to IC, in that case I can find the stability factor. So this term will be 0 plus L IB over del IC RTH plus 0 plus IE equals to IB plus IC, and it will be 1 plus del IB over del IC. Okay, and it will be R equals to 0. So now I can find the term that is equals to del IB over del IC, and it will be 1 plus RE equals to minus RE. Okay, and finally we can get this term, this relation del IB over del IC equals to minus RE over RE RTH. This will be RTH plus RTH. Is that clear to you now? Whatever I have did here?
Yes, sir. Yes, sir.
Okay. So this term, this factor, I just wanted to know about that del IB over del IC that I got from this differentiation. And on the next turn, if I just want to calculate this stability factor, directly I can put this stability factor del IB 1 plus beta over 1 plus RE over RE plus RTH. Okay, and you know well what is the value of RTH? This is R1 R2 over R1 plus R2 in case of potential divider biasing. Okay, fine. And the most important thing, this is beta here. Okay, this is beta, and this term is negative, so I this becomes positive. So now for good stability, S should be 1. Okay, S should be 1. If S equals to 1, in that case, in that case we can say particular biasing is perfect. So for being this factor 1, we need to put this value RTH. RTH must be much smaller than RE. Okay, for S equals to 1, RTH must be much smaller than RE. If RTH is much smaller than RE, in that case this numerator will be cancelled out by this denominator. This whole total dividend will be near about 1. In that case 1 plus beta upon 1 plus beta, it will be approximately 1. Is that fine?
Yes, sir.
So whatever is the
Yes,
resistance
sir.
RE, that resistance must be much greater than RTH for higher stability of potential divider bias circuit. Question: find the stability factor for all the biasing of BJT. This is question for you. Find the stability factor for all kind of biasings for BJT. Okay, you will solve this, you will find the answers by yourself. And technique, whatever is the technique I have utilized, you can utilize the similar kind of technique. Okay, fine. I don't think there will be any problem. Yes. So now I can go towards that multi-stage amplifier. Multi-stage amplifier. There are several multi-stage amplifier. First one is RC coupled amplifier. Darlington pair. Cascade amplifier. Okay, so we'll try, and many more cascade amplifier is also there. So I would like to explain one by one. First, I'll discuss about that RC coupled amplifier. Okay, RC coupled amplifier. Which kind of biasing is this?
Sir, potential divider biasing.
Very good. Transistor Q1, transistor Q2, its output is taken and then applied to the input of another transistor, transistor Q2. So two common emitter configurations, two BJTs with common emitter configurations and potential divider biasings are connected together to make RC coupled amplifier. Okay, and this is input, this is input, and this is Vi, this is Ri, this is CCI, and here we collect output. This is also coupling capacitor at output, and we take output at the load resistance RL and Vin, and this is emitter resistance as usual R1, R2, R1, R2. Emitter resistance, you take a capacitor here, this is called emitter bypass capacitor, and this is RC, this is RC, and again we take another emitter bypass capacitor here, this is CE. This is RC coupled amplifier. Now can you make this circuit by yourself? This is very easy. We have taken two potential divider biasing, we connected together. Input of output of first amplifier is given to the input of second amplifier. This is the only difference. Okay, I don't think there is any problem. This is AC circuit, and if I say you to draw the DC circuit, then what will you do? Tell me.
Remove all capacitor.
Remove all capacitors. That's the point. It means this point will directly be connected to here, and all the capacitances will be removed. And I hope you know the meaning of coupling capacitor and emitter bypass capacitor. Okay, do you remember? Deepak Darak. Capacitors are used to block the DC components and behave as short circuited for AC supply. This is the use of coupling capacitor. This is the use of emitter bypass capacitor. Emitter bypass capacitor is used to bypass the heavy current at emitter terminal of the transistor by providing a low resistance path through it. Okay, I hope you will keep this in your brain forever because I am going to ask these questions in the examination. Okay, so fine. This is first RC coupled amplifier. If gain of this RC coupled amplifier is beta 1 and this is beta 2. Okay, so I hope you can calculate the output of transistor 1 and you can calculate the total output of this transistor by your analysis. Fine. So second one is Darlington pair. What is that? Simply, this is kind of fixed bias network. Let me show you, but little bit different ammeter. This is RL. This is B output. This is common collector configuration. Do you remember? This is transistor Q1. This is transistor Q2. Fine. And if gain of this transistor is beta 1, if gain of this transistor is beta 2, and this is supply plus VCC. This is resistance RB. Okay, so you think here we are collecting output at emitter terminal and collector is common. So this transistor is connected in common collector mode. So this is and this transistor its output of first transistor, you say this output of transistor Q1 is taken and it is applied at the input of second transistor. It means we are collecting output at emitter terminal of transistor Q1. Also we are collecting output of transistor Q2 at emitter terminal and collectors are common. You see collectors are common. So this is called CCCC configuration. Common collector configuration. Okay, and you know what is the important thing about this Darlington pair? Here, if transistors, first transistor's current gain is beta 1, second transistor's current gain is beta 2, then total current gain of Darlington pair will be beta 1 multiplied by beta 2. It is the main advantage of using this total because you see here like if this is IE2 and this current is IE1, so IE1 and this current is IC1, this current is IC2, this current is IB1. Okay, So IE1 equals to IB1 plus IC1, and this IB will be equals to IE1, IB2. So let me write it here. IB2 will be equals to IE1, and that will be equals to IC1 plus IB1. Okay, and here you can write it IC1 1 plus beta 1, because IC equals to beta IB1 IB1 1 plus beta 1. I don't think there is any problem. Okay, this is IB2, and if I calculate IE2, then IE2 equals to IC2 plus IB2. Okay, and here this will be IB2, this is IC2 plus IB1 1 plus beta 1. Okay, fine. And here this current is, since this is base current and this is IC2, and you can write this beta 2 IB2. So you can rewrite this equation, IE2 equals to beta 2 IB2 plus IB1 1 plus beta 1. And if you approximate, since this base current value is very small, if you approximate this whole expression, then in that case it will be equivalent to beta 1 and beta 2. You can think of it. Okay, well, this is fine. And that is fine. Is cascade amplifier. And whenever you will be studying analog circuits in your third year or second year, you will study similar kind of circuits like Darlington pair, RC coupled amplifier, and cascade amplifier with the high frequency analysis. Okay, so in that case, you have to study these all circuits by yourself again. And one more thing, whole analysis whatever you are performing here, you have to perform at the big level. So keep studying this network, these whole circuits, and try to with a great efforts, and also try to do some exercise related to these circuits by yourself. CE, this is RE. Capacitor, coupling capacitor, this is R1, this is R2, this is R3, this is transistor Q1, this is transistor Q2, and here you will collect the output. This is load resistance. Okay, this is called cascade amplifier. This is RC. Okay, and this is RE. Okay, fine. You see here, this is emitter terminal. You are collecting output emitter terminal, and you are utilizing that output of one transistor to as supply or to another transistor Q1. Okay, understood? It means if you see separately, this circuit is just providing loading network to transistor Q1, and rest of the thing is like potential divider biasing. Here this transistor is in potential divider biasing. The difference is this network is only applied here for as the loading, or we can say this is the common collector configuration and this is common emitter configuration. So this is called CCCE configuration. You will study this, don't worry. Okay, and so you can study the equations. Okay, we'll go for small signal analysis. After all, this is multi-stage amplifier. Next, that is fine. So these three configuration, you just keep this in your brain, and related analysis you will perform in the next courses. Fine. So don't worry about that. This is more than sufficient because you are in first year now. Right now, this is more than sufficient. And here BJDC analysis, chapter 3 and chapter 4. Fine. So chapters numerical you have solved, I think.
Yes, sir.
Yes. Chapter 2,
Yes,
3
sir.
and 4. Yes. Chapter 2, 3 and 4. There are three chapters remaining. So this is your assignment. Problems of chapter 2, 3 and 4. Okay, and time required for solving today is the 5 February. So I'm giving you 10 days, 15th Feb. Okay, that is fine. I think this semester is on till 26th Feb, so I'll give you third assignment after that. After 15th till 15th Feb, you have to submit these numerical problems of these three chapters 2, 3 and 4. Okay, because you have already finished that chapter 1's numerical, in that case it will be very easy for you to understand the numerical problems of chapter 2, 3 and 4, and these are less in numbers as well. Okay, any doubt, any problem?
Sir, solve and unsolved both.
Both.
Okay.
Sir,